Hello, everyone. Good afternoon. Can you hear me? Great. So we have a couple announcements. I want to remind everyone that we have the quiz 4 is due on Wednesday before class. So you have 2 more days left to take quiz 4. I checked and we only have 16 attempts, so make sure you check that out. And you know, I think you can kind of just open it, and over time you can refine your answers. You know, you can I think you can keep it open kind of as a draft, and then once the time expires, it just gets submitted. I think that's how it works. And then programming project 2 is due on March 19th, which is 11 days from now. So you got 11 days left on lab 2. And so try not to wait till the last minute on that in case you get stuck. Okay, also, I wanted to also point out, I haven't said this before, I should have. If any of you have any comments about the course or the way that we're doing the online course, or the level of interaction with the TAs and you guys, or the lectures, let us know. Feel free to send us feedback at any time, please. We're obviously, this is new to me, and it's not even like I've done it the same way over the past 3 semesters. I've been changing it up because last fall, I think I might have mentioned this, but last fall we finished the semester after having done a lab course online, adapted my 611 course to do online, and I felt pretty pleased with myself right after the semester ended. I talked to Philip and Charles and said, fellas, I think we did a pretty nice job getting this lab course online. I think we should pat each other on the back. And then we got the surveys back, and it was like, this course was a complete waste of time with a professor who couldn't care enough to do anything more than post a YouTube video once a week, reading off slides that hardly relate to projects. And I was like, oh no. And it was like, really super low scores on there, much lower than I've ever gotten before. 3.5 out of 5, which I'm usually at like 4.775. So, and I had no idea. Like I had no idea that that a majority of the students were miserable in that class. So yeah, I mean, if there's anything you're unhappy about, please, or if you have any suggestions, please let me know. I think the problem is that when I'm in front of a classroom lecturing, I'm pretty good at kind of reading just the expression off of everyone's faces. I kind of know how everyone feels when I can interact in person, but doing it online, I really have, I have no information at all. I'm totally cut off. So let us know if you have any issues or any concerns, so we can make adjustments. And hopefully we'll be back in the classroom in the fall. It's starting to look better. There was a press release today. The university says we're going to go back. They said that last fall though, but now we've got the vaccine appointments and such. So of course no one knows if the vaccine works, but hopefully things will go back to normal. Okay, so let's share. Okay, so today I'm going to finish up real-time scheduling. I'm going to maximize this window because this time I kicked the resolution down on my monitor to 1080p. So hopefully you can see the whole slide. Charles, can you see the whole slide here?
Looks good to me.
Okay, good. Yeah, so that's the key is to not use 4K, because 4K has only been out for 9 years, still pretty new. So Okay, so with the real-time scheduling stuff, I was talking about periodic scheduling algorithms, and this is generally, real-time operating systems are generally going to be designed for periodic tasks, and periodic tasks are generally going to be for control, for doing things like that you would do in a cyber-physical system. The assumption here is that we have one CPU and a set of tasks. Each task has an execution time in a period, and the task has to finish by its period. So you have to be able to sustain task throughput according to the period. And we're also assuming that we can preempt tasks that are running, because if you can't preempt tasks, that makes this problem go from impossible or near impossible to really impossible, basically. So we're assuming we can preempt. The objective is to find a schedule where no task misses its deadline. So one way to characterize the workload or the task set is to calculate its utilization, which is just a sum of the ratios of execution times to periods. So in this case, the 4 tasks I have shown here on the slide, the utilization is over 100%. So this will never work on one processor. It's not schedulable. Then we talked about earliest deadline first, or EDF scheduling, which is when you give the task that has the earliest deadline the CPU, and rate monotonic scheduling, which is where the task with the shortest period has the CPU. Now that's assuming, of course, you give the task that is ready and has the shortest period the CPU. Remember, ready means that it hasn't completed execution for its current period. So what's the problem there? So EDF, pretty straightforward, except the problem, and it works well. In fact, it can execute any task, and it could execute any task set as long as on one CPU, as long as the utilization is under 100%, or less than or equal to 100%. So that's pretty nice. Why not just use that? Well, it's because it's very hard to implement in practice, because you've got tasks whose priorities are a function of time, essentially. So the priorities of the tasks are all constantly changing as time marches on. And so that's a lot to keep track of. It's not really feasible. Rate monotonic scheduling assigns a priority to the task that's essentially just equal to their period, assuming, of course, that lower priorities are more priority. And this is not necessarily always schedulable if your utilization is less than 100%. That's the downside. The upside is that the priorities are static. So in this case, I'm showing the 3 tasks, and looks like these 3 tasks all meet their deadlines, right? So task 3 has the shortest period, 20 milliseconds. So task 3 gets the CPU at the beginning of each one of its periods because it has the highest priority. Task 1 has the next highest priority. So you can see the task 1, right? Task 1 has the next highest priority, has 40 millisecond period. So it generally goes after task 3 finishes. You can see that. And then task 2 has the lowest priority. And you can see the task 2, because it has a lower priority, it does meet its deadlines, but you can see that it often will be interrupted in the middle. So it runs for a little while here in its first period, and then it gets put to sleep, and then it has to run, or sorry, not put to sleep rather, but it has to surrender the CPU for task 3, and then it gets the CPU again. So in other words, it doesn't get to execute without interruption, but that's fine. It still finishes its workload every period. And that was with in this case, we have a utilization of 80%, which would be 10 over 40 plus 15 over 50 plus 5 over 20. Okay, so the RMS, the problem with RMS is that you want to know if a given task set is schedulable, and this turns out to be a pretty difficult problem. In fact, there's no real good way to do this. We have a test that will give us sufficient conditions, meaning that if the workload meets meets this test or passes this test, it's guaranteed to be schedulable. But if it fails the test, that just means that it may or may not be schedulable. We don't really know. That's the problem. And there's really, as far as I know, there's no way to know. I mean, because you could say, well, why not just simulate? Just simulate it. Just try it. Even that's not a good solution, because when the periods are not multiples of one another, you would have to, I mean, you could simulate it, but you'd have to simulate it for the least common multiple of all the periods, and that might be a really long time, depending on the number of tasks you have. So yeah, that's the problem. I'm not even sure. I'm not 100% sure that would work. But anyway, the sufficient conditions here are you multiply 1 plus the ratio of execution time over period for each of the tasks. You multiply those together, and you're checking to see if it's less than or equal to 2. So in this case, it was 1.95. In this case, it was 2.33. So it means that the task set on the left is guaranteed to be schedulable with RMS scheduling, and the task set on the right may or may not be. Okay, I mentioned there's a caveat here. If the tasks are, if the periods are mutually harmonic, meaning that if you sorted them in order of their period, then each period would be, you know, multiple of the period before it. Then then it's okay. You can achieve up to 100% utilization. How often is this the case? I don't know. I don't think it's that common. Okay, then the last topic here was multiprocessor scheduling. This is even harder. This is pretty tricky. There's 2 approaches. There's partitioned scheduling, which is where you basically decide which tasks are going to be executed on which processors, and then you just treat each processor and its associated tasks using a uniprocessor scheduling algorithm. Right? That seems pretty straightforward. That seems easy. The problem is that it's not, because there's lots of ways that you can assign the tasks to the processors. Now, if it's if you don't have that much workload, then there might be, it might be feasible to do this, because if your overall utilization is very low, then it could be that out of the n to the m ways to assign tasks to processors, there could be a whole lot of those that give you a valid way to do partition scheduling, in which case you just pick one and you go with it. But as you might imagine, it's more often the case that the utilization is high, because remember, this is an embedded system. This is for a purpose-built system. You're not going to want to spend more money than you have to. You're not going to want a processor that is more powerful than you need it to be. So it's probably going to be the case that your utilization is going to be fairly high. Another approach, aside from partition scheduling, is global scheduling, where you allow any task to be assigned to any processor. So in global scheduling, you can use RMS. Well, there's a variant of RMS called rate monotonic first fit periodic scheduling, and basically you just go through each task in order, and you assign each task to the first processor, whose current task set associated with it passes the single CPU RMS schedulability test. So in other words, this is a greedy algorithm where you add one task at a time to the task set. Or sorry, scratch that. This is a greedy algorithm where when you have a task that's ready, then and it has the highest priority, or potentially the second highest priority, because you may already be running the task with the highest priority on the other processor. But basically, whenever you're ready to make a decision, a scheduling decision, which is generally going to be at the beginning of a task period, then you assign that task to the first processor that passes the single CPU RMS schedulability test with the other tasks that are currently assigned to it. So that's kind of implementing that is tricky. We're not going to ask you to actually implement that or write that. The important thing here is the schedulability test, which has been proposed for this, which is basically, it's actually pretty simple. You just calculate the utilization as you would, and the normal utilization, which is the sum of all the ratios of execution time over periods, and you check to see if that is less than or equal to m, which is the number of processors, times square root of 2 minus 1, which is about 0.41. So it's basically just normal utilization. Check to see if it's less than however many processors there are times the 0.41. And again, this is a sufficient conditions test. So it's guaranteed to be schedulable if it passes the test. If it fails the test, it may or may not be schedulable. So I have one example here with some 2 CPUs and 4 tasks. Utilization is 76.5. Now, actually, on one CPU, those would be schedulable, because if you do the 1 CPU test, it passes. For 2 CPUs, your utilization has to be less than 0.82 for 2 CPUs, which in this case it is, because it's 76.5. Now you might say, why 0.82? It's because it's the 0.41 times 2, because we have 2 CPUs. I have another example here where we have a 78% utilization, and it would not work on 1 CPU. It would, well, not, I mean, it fails the 1 CPU schedulability sufficient conditions test, which means, again, it might actually be schedulable, but there's no guarantee. But then on 2 CPUs, it would be fine using this algorithm, because the utilization is 78%, which is less than 0.82. Okay, and then finally, this is the last algorithm, is the earliest deadline first. So this is just a straight up implementation of earliest deadline first. This one is a little bit kind of easier to implement, easier to understand, because you would still continuously keep track of whatever process has the highest priority, and you would obviously run that on a CPU, and then the second highest would be on the second CPU, and third highest, and so forth, depending on how many CPUs you have. So this one is this one's got a really strange test, though. I'm not sure. I haven't seen the derivation of this one. I don't know exactly how this works, how this test was derived. But there's two conditions. So the first one is that the total utilization has to be less than n, which is the number of CPUs, which I had called m in the previous slide. Let me change that to m. Sorry. Change the notation there. So number of CPUs. So and that's what you would probably expect, because the normal EDF test was 100% for 1 CPU. The utilization had to be less than or equal to 100% for 1 CPU. The second condition is really kind of strange. You find the greatest common divisor of all the periods, So in this case, we've got periods 40, 20, 12, 40, and 16. I think the greatest common divisor is 4 here, right? Yeah, it should be 4. So 40, 20, 12, 40, 16. It should be 4. 4. Yeah, sorry. I guess the slide has a bug on it there. Oh, I see what happened. Okay, sorry. I see what happened. Okay. I see what happened here. So the table, I think I copied that same. There was supposed to be a difference here on these task sets. Yeah. So let's start with the second example actually first. So you find the greatest common divisor. It's 4, as I mentioned, because you got 40, 20, 12, 40, and 16. So the greatest common divisor of the periods is 4, and so we set that to t. Okay, and then you multiply t against each of the ratios of execution time over periods. So 24 over 40 times 4, 8 over 20 times 4, 4 over 12 times 4. I'm sorry, there's a couple bugs in here. 4 times 4 is 4 over 12 times 4, and then 16 times 4 over 40, and 3 times 4, 3 over, again, this should be 16. Yeah, 3 over 16 times 4. Okay, so let me go over that again. Sorry, so hopefully I didn't confuse you. So you take each of these ratios, 24 over 40, 8 over 20, 4 over 12, 16 over 40, 3 over 16. So you take each of those ratios and you multiply it against t, which is the greatest common divisor of the periods. And you're checking to see if all of those values are integers. Now in this case they are not, because we've got 24 over 4 divided by 40. One of these I updated. Now I'll have to fix this. I'll update this slide and have to re-upload it. I don't even remember which one I changed here, but basically, if any one of these is fractional, which of course at least one of them are, because I think only one of them I screwed up, then it's not. Then it breaks the second condition, and so there's no guarantee it'll be schedulable. So that's the deal with the second test. Now in this case, in the first example, I can tell from, see, 15, 40. Yeah, I can tell what happened here. So that should be 15, 40. This should be 10, 20, and 40. There we go. Okay, so I got it fixed now. So in this case, the least common multiple of the periods was 5. So I multiplied 5 times each of the ratios. So 24 over 40, 8 over 20, 4 over 10, 16 over 40, 3 over 15. And in this case, these guys all worked out to be integers. So it passed. That's the second condition, schedulability condition. So to summarize, in order to guarantee that the EDF scheduling is guaranteed to be met, EDF condition on multiple processors, the utilization has to be less than the number of processors, which is M here, right? Number of processors. So if there's 4 processors, the utilization has to be less than 400%. 5 processors have to be less than 500%. But then there's this second condition that checks, in which you have to calculate the greatest common divisor, multiply the greatest common divisor of the periods, multiply that against each of the ratios, and you're hoping for those to all be integral numbers. Now, if that seems strange, it's because it's difficult to find tests for real-time scheduling over multiprocessors. So I tried to, yeah. So the important thing here is these tests. That's really all. The important thing is the tests for these guys. Okay. Any questions about that? That's all I've got for real-time scheduling. Didn't have a lot of content for this part, but I wanted to, I wanted to address this because this is something that you would need to be aware of if you were designing any cyber physical system. You're going to have real-time constraints if you're doing any kind of control. Okay, great. Now we'll switch topics again. To our next topic, which is queuing theory. Okay, so to introduce this topic, I thought I would begin with a fun example. Hopefully you'll think it's fun. And this example is partially fictitious and partially factual. Suppose you're part of the design team for the U.S. Navy ship USS Lyndon B. Johnson, which is a so-called electric ship because it runs on oil, but the only thing that actually uses the oil is an electric generator, and everything else on the ship runs off of electricity, including the main propulsion system, the propellers. So everything is electric, kind of like big electric generator. Everything's electric. The Navy wants to fit the ship with a new classified electric weapon called the coaxial baryonic cannon, which fires a dense pulse of charged particles that can destroy incoming anti-ship hypersonic cruise missiles. The problem is that the cannon can only fire if the ship's primary DC power bus, so these ships use DC power, medium voltage DC power. I think they want to do high voltage DC power at some point. So the ship's primary DC power bus must be able to compensate for a 500 kilowatt transient within 25 milliseconds. So it has to be able to adjust to maintain its voltage when there's a 25 kilowatt load put on the system that happens within 25 milliseconds. Otherwise, the cannon's linear particle accelerator won't overcome the Coulomb barrier, and the cannon will misfire. So basically, it requires that, technically speaking, it requires that the pulse width modulation duty cycle of all 18 of the ship's modular multi-level AC-DC converters, because the generator on the ship, electric generators, all generate AC power. And so everything on the ship runs off of DC, so you have these AC to DC converters, all of which need to be controlled because the DC voltage will change on those converters once you put a load, unless you update the control signal, which the control signal is a PWM signal, which we talked about earlier this semester. So it requires that the pulse width modulation duty cycle of all 18 of the ship's modular multi-level AC-DC converters, they have to respond to the cannon's load within the 25 milliseconds of the fire command sequence. So the Aegis fire control computer, which controls the cannon, and the AC-DC converters the converters are going to be distributed uniformly along the ship's hull, inside the ship's hull, but along the ship's 610 foot length. So they're spatially distributed throughout the ship. So the converters and the computer are interconnected via a shared packet switch network. So the network is, like any network, is comprised of a grid of routers that have buffered input and output ports. And so when you're at the dry dock working on the ship and testing it out, you determine that you can reliably send and receive data on the network at 10 gigabits per second. But you notice that the packet transfer time seems to increase as the network traffic load increases. Now, you don't understand why this is the case. And you're concerned because you don't know if there's any way to determine the maximum packet transfer time or to bound the packet transfer time. Basically predict the packet delay. And ideally, you'd like to be able to guarantee a round-trip delay of less than 25 milliseconds, regardless of what else is going on in the network at the time. Otherwise, the cannon won't fire. The controllers won't be able to maintain the voltage under the load, the pulsed load. So if you can't guarantee this, then the ship will need to be commissioned without its cannon leaving its carrier strike group defenseless against hypersonic threats. Okay, so the answer to all this is queuing theory. Queuing theory is the mathematical study of waiting in lines. Why should you care? Why should a student who's studying systems engineering or cyber-physical systems care or need to know about waiting in lines? It's because whenever you send a message from one digital system to another, so this could be between computers or between chips on a circuit board. Anytime you do that, when both systems have a different internal clock, this is technically a distributed system. And so anytime you do that, you're going to have to go through some kind of a FIFO just to cross the clock boundary. And also this happens whenever you send a message, whenever you can potentially send a message to one device from more than one source. So in other words, whenever you have a shared resource, then you can potentially have to go into a queue and wait to get service. So queuing theory describes the behavior of a system that is depicted here on the slide. Hopefully you guys are seeing that slide, right? You guys can see the slide, right? Just making sure. I just got paranoid all of a sudden. Okay, yeah, sorry. Great. Yeah, sorry. I don't know why I got paranoid all of a sudden. I thought for a minute you might not have seen it, that I might not have switched to it. Okay, so yeah, so the queuing theory is describing a queuing system. What's a queuing system? It's what I'm showing here on the slide. It's where you have a service facility that includes a queue and servers. And then you have requests that come in externally that go into the queue, and then the servers will take requests out of the queue and service them, and then at some point the request will complete service, right? Notice also that there's these down arrows here. There's a down arrow here outside the system, and there's a down arrow coming out of the queue. And this is intentional. This describes situations where sometimes the queue requests will leave before entering if the queue is too long. It's possible, depending on the design of the system. Or sometimes requests will drop out if they wait too long in the queue, which would make sense in a real-time system if basically if they've missed their deadline, then there's no point in servicing that request. Now in this course, we won't consider that behavior. We're going to try to look at the simpler situation where we don't have requests that give up if they have to wait too long. So the queuing system might have multiple servers with one queue, which is what I showed on the previous slide, or you might have one queue per server, as I show on the right. And again, in this lecture, I'm going to focus only on the first case. But the point of this is that there are different ways that you can model a queuing system. And then when you go to analyze the queuing system, you have to obviously adapt the mathematics to be consistent with the model. We're going to consider the simplest case here, where you have one queue and actually just one server. So what does queuing theory tell us? What's the objective of this? What is it good for? Well, it tells us how long a message is expected to wait, either in the queue or in the system. So you can actually decompose it into the queue waiting time or the system waiting time. System waiting time is the time it's in the queue plus the time it's being serviced. Generally speaking, these times are all random variables. You can also use it to determine the number of customers. When I say customers, sometimes I'll say customers, other times I'll say requests. But In the queuing theory textbooks, they'll often refer to a request as a customer. But I usually call them requests because I think of it as like, you're sending a request to a peripheral or something, or you're sending a packet to request something of a peer on the network. And then you can also use it to calculate the idle time of servers. There's a lot of things that you can. It's a way to analyze a queuing system, basically. So as I mentioned, there's in the first couple slides, the queuing systems have different characteristics. You have to assume that there's an arrival pattern of customers, and this will be dependent on the system, the application that you're designing. But basically, the idea is that when I say pattern, I'm talking about the probability distribution of the time between successive arrivals. So these are you can use different probability distributions for this. In this course, we're going to focus on using the exponential distribution. And in the exponential distribution, you've got this idea of rate. So you have this kind of average rate that customers arrive, and based on that rate is a parameter for the statistical distribution that will allow you to model the time between arrivals. So if your rate is really high, then it's much more likely that you're going to have a very short time between arrivals. If your rate is lower, then you're going to have, obviously, it's more likely you'll have longer inter-arrival times. You can also have, you can support single or simultaneous arrivals. In this case, we'll just focus on the simpler case, single arrival at a time. So only one thing can come in at a time, one request. And then stationary or non-stationary is whether that pattern may change during operation. Obviously, we're going to focus on just the stationary case. And impatient customers are the ones I described that will leave if the line is too long. And then the service times are also stochastic, meaning random variables. So the time it takes to service a request is also something that you would model as a random variable. And you can also have single or simultaneous service, meaning the number of servers. You can have multiple servers that can get requests simultaneously. We'll just consider the single case. And then the number of servers and the number of service channels, obviously. And then there's system capacity, which is if you have a limited queue size. In this case, we're just going to assume an infinite queue size for the time being to simplify this. I just want to give you an introduction to queuing theory. You could teach a whole course on this. And then queue discipline, which is the way the queues work. In almost every case, queues are first come, first serve. They're a FIFO. But there's other types of queues. You can have, last come, first serve, random, polling, priority schemes. We're just going to handle we're just going to assume the first come, first serve. And then you can even do crazy things like you can have server stages where, you have to go through multiple stages of servers. And that's probably the most advanced way to model one of these things. So queues they have this naming scheme, this notation that attempts to take all of this information that I just explained and package it into a 5-character sequence separated by slashes, forward slashes. So and you may say, wait a second here, didn't you go through 6? You went through 6 things, right? So why is there only 5? There's only 5 items here. The 6th thing was the server stages. I don't actually know how that information is described in this notation. So that's the one that's missing. But basically, each one of the things I mentioned has one of these slots where I have A, B, X, Y, and Z. So A and B are a letter that represent the arrival time distribution and the service time distribution. So that can be MGD, EK, HK, or PH. So G is general sorry, M is for exponential. That's the one we're going to use. You might say, why M? Well, M actually stands for Markovian or memoryless, but both of those are just another way to explain exponential distribution. They're the same thing. G is the general distribution. D is deterministic. E sub k is for Erlang type k. H sub k is for a mixture of k exponentials. And pH is the phase type. We're only going to be discussing exponential. And then X is the number of parallel servers. Sorry, clarify. In this course, we're only going to cover the M type for the arrival and the service time distribution. So we're going to be covering queues that start with MM. And then M, the X there is the number of parallel servers. And we're only going to consider one server. So we're going to be using MM1 queuing systems, I should say. The fourth slot is Y, and that's the system capacity, which is the maximum number of requests that can be in the system. In our case, we're going to assume that it's infinite. Now, if you have infinite service capacity, then you can omit the fourth slot there. And then the fifth slot is Z, it's the queue discipline. And in my experience, the most commonly used one is, as I mentioned, is first come, first serve. And if it is first come, first serve, you can omit that last slot. So basically what that means is that we're going to be targeting the MM1 queue, which you might have heard of before. The MM1 is kind of the most common type of queue or queuing system. But this is, this slide shows you how you can decode other types of queuing systems. Okay, so a lot of one of the fundamental concepts in queuing theory is Little's law. A lot of queuing theory is built on this idea, which is actually just a very simple relationship between the average arrival rate of requests or customers and the average time that a request spends in the system. Now, this is just the whole system. This includes both the the queuing time and the service time. This is kind of abstracting those away. So this is the time in the system is W, and the arrival rate is lambda, and the average number of customers in the system is L. So Little's law is just L equals lambda W. Now you might think, at first you might think, well, where the heck did that come from? Well, if you look at this example, it becomes really clear. Actually, so let's say you have an elementary school with 6 grades, and every year 30 new students enroll in the first grade, and so lambda would be 30 students per year. That's the arrival rate, and the students progress through the successive grades and leave upon completing the 6th grade. So in this case, W is 6 years. What's the total number of students enrolled in the school, which would be L? Well, it's easy. It's L equals 30 times 6, 180 students in the school. So that, when you think of it that way, that's pretty simple. I mean, that's pretty much what you'd probably think if someone asked you this question. That's probably the idea what you come up with. Okay, so we'll come back to Little's law because it turns out that when you derive the behavior of these queues, usually the last step is applying Little's law. But before we get to that, we'll come back to that. We have to talk about this exponential distribution. So hopefully you probably know this really well, having taken Stat 509. You should be comfortable with the exponential distribution. You probably should have taken 509 recently, or you might be taking it now. I don't know. But, it's a distribution that has only one parameter, lambda. So it's lambda again. Lambda is you think of a normal distribution, you have the mean and the standard deviation. With an exponential distribution, you just have the one parameter lambda, and it's the rate. And you could think of the rate as literally having a units of events per second, right? Or events per unit time, rate, lambda. And so now you can still calculate the mean though. The mean of an exponential is just simply 1 divided by lambda. So lambda is the reciprocal of the mean or the expected value. But whereas the mean is kind of a parameter for like a normal distribution, it's kind of the lambda is the parameter for the exponential. So you can get the mean from the lambda, but lambda is your parameter. And so the probability density function of the exponential is lambda e raised to the negative lambda t power. Now, the weird thing about exponential is that it's actually not defined for t less than 0. Now, t has to be 0 or positive, and lambda also has to be greater than 0. So there's a weird restriction on this that the other distributions don't have this kind of restriction. So what is the probability density function? What the heck does that mean? I used to think, well, I mean, it's been 25 years since I had my Stat 509. So I don't remember a lot of this stuff. I used to think, though, even after I took that, I used to think of the probability density function as the probability that of a given value, in this case of t, which is the input. But this is not correct because this is a continuous function. And the probability of a specific value of t, like if you pick a value of t, is actually basically 0 because it's infinitely small, I should say. It's more accurate. Because there's an infinite number of possible values that an exponential random variable can assume. So like it's not as if you can like plug 2 in for t and get the probability of 2 showing up, because that's probably never going to happen. You'll never see 2.0 show up. You might see a value close to 2, but nailing exactly 2 on a exponential random variable is essentially the probability is basically 0. So if that's not the case, like if I plug 2 in and I get a certain probability, then what the heck is it useful for? What does it mean? Well, it turns out that the PDF is actually giving you a relative probability, not an absolute probability. So what that means is that if you evaluate another value in the same distribution, then you have 2 values, and then you can compare them, their relative probabilities. So, for example, if I put in a value, let's say I take a value of t, I stick it in there, and I get 0.2. There's a 20% chance. And then I get another value, and I plug it in, and I get 10%. What that means is that the second value, or sorry, the first value, rather, was 20. The second value was 10. The first value is twice as likely to show up than the second value. So that's what a relative probability is, as opposed to an absolute probability. It's only useful for comparing 2 values inside that you're evaluating, right? Okay, so I mentioned this earlier, but lambda is the rate, and so I have a plot there on the right-hand side that shows the probability density function. As I mentioned, it's only defined for values greater than or equal to 0, so you can't go below 0, so the plot starts at 0. And then I've got 3 lambdas on there, 0.1, 0.4, and 1.2. And as I mentioned, that those represent rates. And so you're basically translating a rate into the probability between successive events happening at that rate. So a higher rate, 1.2, which is the yellow line, higher rate, means the time between events will be smaller. The smaller lambda value, which is 0.1, means that there's an increased probability of larger values. But the interesting thing that happens there as well is you notice that with the lower rate, the blue line, the 0.1 lambda, notice that it's like flat. Basically, it looks almost flat. It looks like a uniform probability distribution, doesn't it? I mean, it slopes down a little bit, but has a very gentle slope. So why is that? Well, it turns out that the variance, you can calculate the variance of this distribution, and it's 1 over lambda squared, which means that the variance scales up with smaller values of lambda and scales up a lot, scales up, as a function of lambda squared. So in other words, as we decrease lambda, the variance shoots up. And it shoots up because the distribution becomes flatter. Basically means that if you have a very low rate, then you're going to see all kinds of wildly different delays happening between events. Whereas if you have a very high rate, then you're going to see a little bit more consistency. The events will happen more consistently close together. So that's basically what, that's the whole idea behind the exponential distribution. Then there's a cumulative distribution function, or CDF. Notice it's not density now, it's cumulative distribution. So the D stands for density for the PDF, and it stands for distribution for the CDF. And the reason for that is because the CDF is much more useful because you can actually plug values into the CDF and actually get probabilities out. So it's an absolute, you get an absolute number out of the CDF. And it gives the probability that the random variable will be less than or equal to the value that you're plugging in. So you pick a lambda, and you say, okay, what's the probability that the random variable will be less than or equal to 10? And then you plug that in for t, and you get a number. You get a probability, an absolute probability. So this one is 1 minus e raised to the negative lambda times t. And then you've got the complementary cumulative distribution function, CCDF. And this gives this is a distribution. It gives you an absolute probability. And it's the probability that the random variable will be greater than the value that you're testing, that you're plugging in for t. So this one is, mathematically, it's the simplest one. It's just e raised to the negative lambda t power. So that's that one's pretty easy, I think. Okay, so let's look at some examples. Assume we have an exponential random value called t. We've got rate 3. Now you might say, oh, come on, we've done so many of these in Stat 509. But I just want to point out kind of a sanity check here, right? So imagine you have a request coming in at 3. Lambda is 3 events per second, average 3 events per second. All right. What is the relative probability of t equals 2? T being, the value of t being 2. Well, that's just 2 times e to the negative 3 times 2 power, 2e raised to the minus 6 power. Now think about this. Okay, the answer is 0.5%, but does this make sense? Well, basically 0.5% is really low probability. Basically means it's not going to happen, right? It's very low, very, very unlikely. Why is it very unlikely? Well, it's because, think about it, on average, you're getting 3 events per second, and what I'm asking is, what is the probability that there's going to be a 2-second delay from one event to the next, right? Yeah, obviously very unlikely, right? There's 3 events coming in per second. It's very unlikely that there'll be 2 seconds passing by between 2 events at that rate. So yeah, it makes sense. 0.5% sounds about right. Sounds right. What's the probability of t being less than 2? Well, pretty damn good. Because again, 3 events per second. Yeah, so it turns out it's 99.75% likely. It makes sense, right? And then of course, what's the probability of t being greater than 2, well, yeah, it's 0.25%. So possible, but unlikely. Okay, so the exponential distribution has a lot of really neat properties that I didn't know actually until I started looking into this when I started relearning queuing theory. So let's and by the way, I'm not just presenting these as because they're interesting. All of these properties actually relate to directly how to do queuing theory. You actually build all your queuing theory on top of these properties. Now you might say, well, wait. You said that you don't have to use the exponential distribution though, right? In the queuing theory, you can use other distributions for arrival pattern and the service pattern. Yeah, you could. And you'd have to exploit the properties of those distributions in order to work out the math. So, but we're just going to look at the exponential. Okay, so let t1 to tn be independent exponential random variables, each with a different rate, lambda 1 to lambda n, respectively. And then the minimum value, the minimum of all of those guys is exponentially distributed with rate lambda plus lambda 1 plus lambda 2 plus all the way to lambda n. So in other words, if you have a bunch of variables, exponential random variables, and you want to find out what's the distribution of the minimum value that I can expect of all these as a pool, well, it turns out to be lambda. It's just another exponential distribution, but you're adding up all the lambdas. That's pretty cool, right? It basically, you just add all the rates together, and then you can kind of model all of those guys as one. So let's look at an example of how the numbers work out, and this is pretty neat. I think it's neat. I mean, it's kind of geeky, but assuming you have 10 exponential random variables, t1 through tn, and let's just say all their rates are 0.01. Now, what does that mean? 0.01 events per second. That means that it takes 100 seconds before you can expect to get an event, right? Remember, it's the variant, the expected value or the mean is 1 over lambda. So 1 over 0.01 is 100. So I can expect to wait 100 seconds before I see anything for each one of these guys individually, right? But what's the probability that the minimum value of all of these will be less than or equal to 2? So what's the probability that I'll get one value out of any of these guys? So I've got 10 of these guys all generating values at a rate of 1 per 100 seconds. What's the chance I'm going to see something happen by 2 seconds? Now, thinking about that, if you ask me, I'd say, I mean, there's 10 things generating events at a rate of 1 for every 100 seconds. It's a minute and 40 seconds. Okay, almost 2 minutes, right? There's 10 of them. What's the chance I'll see something by 2 seconds? I'd say, I don't know, pretty low, actually. I don't think, probably won't see anything for, probably I'd say, I don't know, 5%, that's low. Well, you work it out. The probability of any one of these guys, like for example, T1, probability you're going to see something in 2 seconds when you can expect to wait 100 seconds is 2%. That's pretty okay. I'd have guessed a little lower maybe, but 2% sounds reasonable. The probability that any of the 10 will generate an event within 2 seconds is going to be, well, how do we figure this out? Well, you have to add up all those rates. So if you have 10 0.1s, you add them up, you're going to have you have 10 0.01s, and you add those up, you're going to get 10 times 0.01 is 0.1, right? So the rate is now going to go from 0.01 for one of these guys to 0.1 for 10 of these guys. Okay, so now I just calculate the likelihood of, I evaluate the CDF, the cumulative distribution function, with a rate of 0.1 at 2 seconds. So that's 1 minus e to the negative Lambda t is 1 minus e raised to the 0.1 times 10 times 2. Turned out it's 86%. Whoa! I didn't expect that. I mean, that's 86% that one of these guys will give me an event when they're that slow individually. So yeah, that's how that works out. Let's look at a little less. Let's look at another example. The time until a bus arrives is exponential, with a mean of 20 minutes. The time until a taxi arrives is exponential, with a mean of 5 minutes. What's the probability of waiting less than 5 minutes for a bus or a taxi? Okay, so buses arrive every 20 minutes. Taxis are about 20 minutes. It's exponential. Taxi arrives once every 5 minutes on average, exponentially. What's the probability of waiting at least 5 minutes for a bus or a taxi? Well, you got to figure out the lambdas. So the lambda is 1 over, the bus lambda is 1 over 20. The taxi lambda is 1 over 5 because, you know, we're given the means. So hope I did this right. 1 over 20 plus 1 over 5 is 5/20ths, 1/4, right? Yeah, 4. Right, that's right. Yeah. Yeah, 1/4 is the overall lambda. And then so we plug the 1/4 in as the lambda, and we get the 5 minutes as the t. Plug those into the which one? Well, in this case, we use the CCDF, the complementary, because we said waiting at least 5 minutes. So we want to know how likely it is that we're going to be there for 5 minutes or more than 5 minutes. Sorry, more than 5 minutes. So use the CCDF. It's probability that t will be greater than. It's actually, whoops, sorry. That is actually, sorry, I just noticed that too. Greater than, there we go. Greater than 5 minutes. Because if you go back to the, yeah, see, it should be greater than, see right here, greater than, CCDF. So the wording there is a little, at least 5 minutes. That kind of implies that it could be exactly 5 minutes. But anyway, the probability that t is greater than 5 is going to be e raised to the negative 1/4 times 5, which is 29%. 20 seems about right. Not, you know, not too likely, but you know, about a 30% chance. Okay, so you might have also heard of a Poisson process. And Poisson process is a variation on the exponential distribution, and it represents the probability of n events occurring by time t when you have a rate lambda. So you might say, well, wait, what's the difference exactly? Well, Poisson processes are basically an exponential, but instead of characterizing the inter-arrival times with a given rate, it's about counting the probability of how many events occurring by time t. So, but it's also assuming it's built on the exponential inter-arrival times. So, so the idea is that you've got p sub n of t. So n is the number of events, t is the time, lambda is the rate. So the equation is lambda t raised to the nth power divided by n factorial times e to the negative lambda t power. Now, the times between successive events are, you know, I mentioned they're exponentially distributed, which means that they are, I mean, the assumption here is that they're also independent. All the events are independent. So, and I'll talk more about this independence property soon. So let's look at an example. So let n of t be a Poisson process with rate lambda equals 5 per minute. What's the probability that exactly 2 events occur by time equals 3? Okay, well, you know, what do you expect here? 5 per minute. We want to know exactly if exactly 2 events occur by time equals 3. So the probability of, and the notation is a little weird, but capital N of 3 equals 2. We just pretty much just plug in everything. And it turns out that shockingly low, 0.0034%, assuming I didn't screw up the math there. Now, what is the probability that 2 events occur in the interval 3 to 6? And now you might be thinking, well, this has got to be some kind of trick question, right? So we looked at 2 events occur by time equals 3. So basically 0 to 3. And now we want to know 3 to 6. So what's the catch? What's the catch here? There's none, because everything's independent. So what that means is that the Poisson process doesn't depend on anything that happened in the past. So that means that you can consider the Poisson process from 3 to 6 being 3 seconds is going to give you the same answer as 0 to 3. So it's the same. But what's the probability that 2 events occur in the first 3 seconds and 2 events occur in the next 3 seconds? Well, in this case, you basically just calculate the 2 probabilities using the Poisson process there, and you multiply them because you're looking for both things to be true. So you multiply those 2 values. In this case, you're multiplying the same value because it's they're both 3-second intervals. Okay, so yeah, so as I mentioned, the times between the successive events are independent and exponentially distributed, which is what I already said. Okay, so all right, I think that's probably a good place to stop for now. I want to give you guys a chance to go and look at that quiz, because I didn't give you too much time last time. And I want to make sure you get a chance to look at that. I want to encourage you to go and take a look at the quiz. The quiz, of course, is on real-time scheduling, and next week I'll have a quiz on this queuing theory for you. So I'll go ahead and stop there. Do we have any questions? Okay. Okay, I'll fix the typos that I had in the previous slides. I'll repost those. These slides are already posted on Dropbox, and I'll post the lecture as well. And if you have any questions, feel free to contact us. And like I said, if you have any concerns or comments, feedback, let us know. I'm hoping that I don't get to the end of the semester and get another surprise with the survey saying it's the worst course I've ever taken. Okay, great. All right, well, I'll see you guys on Wednesday then. Thank you.